Okay, these are your video notes for section 6.1 on measuring angles. So this is kind of your first introduction formally in your book to the idea of radius. Okay, well let's first start off by talking about what a positive angle is. Okay, a positive angle, that's an angle created with a counterclockwise rotation. So as you see, this angle created by moving this direction is a positive angle from your initial side. Okay, so that would be a positive angle. A negative angle, so positive angles are counterclockwise. Negative angle measures would be clockwise. So if we move in a clockwise direction this way, then that's going to give us our negative angle. Okay, so that would be a negative angle. Okay, so counterclockwise is positive. Clockwise is negative. Okay. I like to think of it if we're going through the first and then second and then third and then fourth quadrant, those are going to give you positive angles. If we're going down towards, going the other direction, fourth quadrant, then third, then second, then first, that would give you negative angles. Okay. All right. So now let's define what a radian measure is. And we kind of talked about this a little bit earlier because we had to learn the unit circle. Okay. If a circle has a radius of 1, right? If we've drawn a circle that has a radius of 1, right? Then a radian, the measure of a radian is the length of the arc. This arc length is equal to the angle. So the distance, the length of that arc that I just kind of drew in black squigglies is equal to the radius, right? Okay, so the angle can be measured in radians. Okay, so that's radian is an angle measure. Okay, the length of the arc that the angle grabs. Okay, if the circle's radius is 1, that's what a radian is. Okay, so another way to think about it, if an angle is 1 radian, so if I have a 1 radian angle, then that means that the arc that it grabs is the same length as 1 radius of the circle, right? 1 radian represents an arc that's grabbed that's equal to 1 radius. So if I have a circle with radius 1, the arc that a 1 radian angle grabs is length 1. If I have a circle that's got radius 2, right, then the arc that 1 radian grabs would be equal to a radius, a 2 radius long arc, and so on and so forth. Okay, so there you go. That's what a radian is. So now we can talk about angles in terms of both radians and degrees. So an angle, we can talk about how many radiuses that circle is grabbing, that angle is grabbing, or we can talk about how many degrees. And you should be comfortable with degrees because that's kind of what you've been using your entire life. But we can convert back and forth between radians and degrees and radians. Okay. And all we have to do to convert back and forth between degrees and radians is set up some known ratio. So for instance, it says, if the question is how many radians is 50 degrees? Well, we know that we have some ratio. If we want to know x radians is the same as 50 degrees, then we can set up some other known ratio. Well, I know that pi radians gets me halfway around the circle. And halfway around the circle in degrees is 180 degrees. So x radians over 50 degrees would be this, have to have that same ratio, consistent ratio of pi radians over 180. And then we can solve this for x, and now we've converted from degrees to radians, okay? So solving that for x, I get x equals 50 pi over 180. And if I reduce, right, that would be x equals 5 pi over 18. So how many radians is 50 degrees? 5 pi over 18 radians is the same angle as 50 degrees. Okay, just set up a common ratio. Radians to degree equals radians to degree. We know that ratio. We could have done 2 pi over 360. 2 pi is all the way around the circle. 360 is also. Either way, a known ratio to the one you're comparing, right? Radians to degrees equals radians to degrees. Okay, let's convert radians, pi over 12 radians, to degrees. How many degrees is pi over 12 radians? Well, if I have x degrees, that's what I'm looking for, x degrees over pi over 12 radians would have to be, now I set up the ratio that I know, 180 degrees to pi radians, right? And then if I multiply both sides by pi over 12 to get the denominator to cancel, right? Then I get x equals 180 over pi times pi over 12. The pi's will cancel, and I'm left with 180 over 12, right? 180 over 12. And 180 divided by 12 is 15 degrees. So how many degrees is pi over 12 radians? It's 15 degrees. Okay, so same thing, converting radians to degrees, you set up a ratio, right? Radians over degrees equals radians over degrees. How do you want to convert radians to degrees? You do the exact same thing. Okay, just set up a common ratio. Make sure that the relative locations are all the same. Like on the second example, the degrees were both in the numerators and the radians were both in the denominators. On the first example I did, the radians were both in the numerator and the degrees were both in the denominator. So either way you go. Okay? All right. All right, let's talk about what are called coterminal. So we got a lot of vocabulary words we're learning here. Coterminal angles. Coterminal angles, that's simply two angles where the sides of that angle line up. So all three of these angles here are coterminal. So for instance, a 30-degree angle would line up with a 390-degree angle. So if I went around positive 390 degrees in this direction, my sides would still land up on top of each other. So a 30-degree angle and a 390-degree angle would end up looking the same as far as where the rays that create the angle are. At the same time, a negative, if we went in the negative direction, a negative 330-degree angle would also be the same. Okay, so how do we find coterminal angles, right? Well, it's pretty simple. In order for the angles to line up, we need to go all the way around the circle. So if we're dealing with degrees and we want to go all the way around the circle so that they line up, we either need to add 360 degrees or subtract 360 degrees, right? And that would land back on top of it. Or you could add or subtract some multiple of 360 degrees, right? You could potentially go around the circle 1, 2, 3 times, right? So that would be adding 3 times 360 degrees to your original angle, right? And you can do the exact same thing with radians. Remember, how many radians is the entire distance around the circle? 2 pi. 2 pi radians is equal to 360 degrees, right? That takes you all the way around the circle. So you can either add or subtract some multiple of 2 pi. You could add 2 pi radians, 4 pi radians, 6 pi radians, 10 pi radians. Regardless, that's just going to take you many loops around the circle, okay? And then you would have a coterminal angle. So that's what coterminal means. That should be pretty straightforward on how to find them, hopefully. Okay, now let's talk about arc length. I don't think I had any more on that here. Let me check one more time, make sure I didn't. Yeah, okay, that's it. Okay, let's talk about arc length. Okay, well, arc length, this is let's say I have an angle that's grabbing a circle, right? And I wanted to know the length of this. That's what I'm talking about when I say arc length. It's the arc that the central angle of a circle is grabbing. Okay. Okay. So if I have a circle of radius r, the length s, this is the arc length. So we're calling s arc length, right? Is equal to r, the radius, times theta. Now theta is in radians. So the length of the arc that I'm grabbing is equal to r theta, where theta is in radians. Make sure theta is in radians. If theta is in degrees, then you are not getting the arc length, right? So S is r theta. Well, that should make sense that arc length is just the radius times the radians of the angle, right? S equals r theta. This is something to have memorized, by the way. Well, that should make sense because remember our definition of radians says how a radian is how many radiuses you can get in an arc length, right? So if S is your arc and R is how many radiuses, right? If I do the math, get theta by itself, the radians by itself, radians is the arc length divided by a radius, the radius of the circle. So, however, 2 pi radians means every single circle, you can get 2 times pi number of radiuses. That will take you the distance all the way around the circle, right? So 6 point whatever is how many radiuses you can attach to the circumference, along the circle. 6 point blah, blah, blah. 6.2 something, right? Okay. All right. So let's say we have a 60-degree central angle and it intersects an arc of a circle with a radius of 2 feet. What is the length of the intercepted arc? So we're looking for arc length. Well, remember, here's our formula. S equals r theta. Now, they only gave us a 60-degree central angle. So the first thing that we need to do is we need to convert our angle from degrees to radians. And if you know your unit circle really well, you already know that 60 degrees is pi over 3 radians, but we'll prove that anyway. Okay, so 60 degrees over x radians would have to be equal to 180 degrees over pi radians. And then we solve it for x. I probably should have put x in my numerator, but that's okay. So to solve it for x, I multiply both sides times x and times pi, and then divide by 180, and I end up getting x equals 60 pi over 180, right? Solving for x. The zeros cancel, like reducing the fraction, becomes pi over 3, right? 60 is 1/3 of 80, 180. So x equals pi over 3 radians. And RAD is short for radians. So that means my arc length S would be pi over 3 times my radius, which is 2 feet. Let me put this in the same order as my formula. 2 feet times pi over 3. Or S equals 2 pi over 3 feet. So that would be how long the arc of a 60-degree angle, 2 pi over 3 feet. And remember, pi is that 3.14, right? So it's a little bit more than 2 feet. Okay, a 60-degree angle is very, very close to 1 radian. It's just barely bigger than 1 radian, right? Because if 60 degrees is pi over 3 and pi is 3.14, right? Then 3.14 divided by 3, that's just barely bigger than 1 radian. So if you want to think about how big is 1 radian really, it's about the same. It's a little bit less than 60 degrees. Just a little bit less than 60 degrees is what 1 radian looks like as an angle. Okay? Anyway. the area of a sector of a circle. So now we've used radians to find, we found arc length, S equals R theta. We found how we can use our radians to figure out the length of a arc on a circle, right? What if we wanted to find the area of a circle? Well, if you remember back from geometry, the area of a circle is pi r squared, right? Well, if we want to know the area of a sector, kind of like a pizza slice, like if here's our circle on the coordinate plane, and we wanted to know what is this area? What is this area right here? This sector of the circle, right? Well, really, all we need to do is think about what percentage of this circle is this blue pizza slice, right? What percentage of the circle is that blue pizza slice? Well, that percentage of the circle is the ratio of the number of radians out of a whole, right? Part out of a whole is your ratio. That's kind of how you get a percentage. So theta radians out of 2 pi. So this would be the area of the sector. The area of this sector of the circle that we're caring about, this blue section, would be theta radians divided by 2 pi, because there's 2 pi radians in a whole circle. So blue out of the entire area of the circle, times, so that decimal, that's the percentage of the circle, right? The ratio of the circle that we care about, times the area of the entire circle, right? So that should hopefully make sense about, how we're solving this. Well, the pi's are going to cancel here, right? And we're left with, if I, rearrange some things, right? Area of a sector, I should say sector. The area of a sector of a circle is 1/2 r squared theta. Once again, theta is in radians. So make sure you're using radians. So the area of our sector of a circle is 1/2 r squared theta, where theta is in radians. Okay? If you have that formula memorized, this can be really easy. And if you don't have the formula memorized, it's not that big of a leap to come up with this formula there, right? What percentage of this circle am I caring about, right? Radians divided by 2 pi times the entire area. That's the same thing, okay? All right. All right, so let's talk about, continuing on, let's talk about linear speed and angular speed. So linear and angular speed. And interestingly, those of you that have had physics already know this, the difference between speed and velocity is direction. So the difference between speed and velocity, velocity has direction. Velocity indicates a direction, which means if we're talking about velocity, it has a sign. So like you can have a positive velocity or a negative velocity. You cannot have a positive speed or a negative speed. Okay, speed is always positive because it doesn't indicate direction. Okay, only velocity indicates direction. But our formula for angular speed is the same formula we have for angular velocity. It's just if you're finding an angular velocity, you can use negative radians because that would indicate a negative angular direction. But for speed, radians will always be positive. Okay, so don't stress about this. Your angle will always be positive. Whatever it says, however many radians, that's what you're going to put in. Okay, and think about this. Angular speed, what we're talking about when I say angular speed, that means how quickly we're traveling. The radians change as we travel around the circle, right? Okay, so how quickly radians, think about the units of angular speed, radians per time, like seconds, radians per second. How quickly our angle is changing as we go around the circle, right? How quickly our angle changes. That's what I mean by angular speed. okay? When I talk about linear speed, we're not talking about the angle changing with time. Linear speed is just distance per time, right? So your arc, like the actual distance traveled divided by time. So those are two different things that can measure, and you can think about the same kind of idea. So they're related to each other, but they're talking about a slightly different thing. How quickly we go around the circle, right? How quickly we go through 2 pi radians. That's one full rotation per time. That would be angular speed, right? Linear speed is the distance, the physical distance we went per unit of time. Okay? And those aren't always, they're not the same thing. I hope that makes sense. Okay? But they are related to each other. So if we compare the two, we can convert back and forth between linear speed and angular speed. Okay? Remember, v we're using for linear speed because we're not giving it a direction. Our linear speed is the radius of the circle times the angular speed. Okay, radius times angular speed is linear speed. And there's a very simple proof of this in the book, but in the interest of keeping the video shorter, I am not going to prove that this is how you convert your angular speed to linear speed. But that proof is in the book. It's really simple. It's like 3 lines. So if you're curious. All right, so let's do an example where we convert, let's do an example. And this is an example that comes in your book. Okay, the speed of a current, to measure the speed of a current, scientists place a paddle wheel in the stream and observe the rate in which it rotates. So you put a wheel in a stream and observe how quickly it rotates. If the paddle wheel has a radius of 0.2 meters and rotates 100 revolutions per minute, right? RPM is revolutions per minute, right? Find the speed of the current in, this is important, meters per second. So we want to, we know we know the angular velocity, the angular speed. We know it's going 100 revolutions per minute. And we want to change that to figure out what is the speed of the current. Okay. Well, remember, speed is the distance, is how quickly this paddle goes along this distance along the outside here. That's what's per unit time. That's what speed is. Angular speed is how quickly our angle, our radians change. And so we know we're going 100 revolutions per minute. Well, 100 revolutions per minute is the same thing as 2 pi, that's 1 revolution in radians. 2 pi radians times 100, that's how many radians we travel in one minute, which is 60 seconds. Okay, so this would be our angular speed, right? How many we did? We went through 200 pi revolutions per 60 seconds. That's my angular speed. So let me just go ahead and convert that. That would give me 200 pi over 60, which would reduce to 10, let's see, 10 over 30, 5, 10 thirds pi. So 10 pi over 3 radians per second. That's how fast our angular speed is. Our omega is 10 pi radians, 10 pi over 3 radians per second. Okay, so that's how quickly we're going around the circle, right? All right, now we need to convert our radians to velocity, not velocity, speed. So speed here, v, would be equal to our angular velocity times radius. Remember, here's our formula, r times omega. So the radius here is 0.2 meters, 0.2 meters, times my omega, which was 10 pi over 3 radians per second. Okay, and remember 0.2 is the same as 1/5, so that means my velocity would be the same thing as 10 pi over 15 meters per second. 0.2 is the same thing as 1/5. That's just so. Then if I reduce that, my velocity would be 2 pi over 3 meters per second. Not my velocity, my speed. Sorry. So there you have it. Okay, so those are our video notes. I hope this made sense. That covered a lot of stuff, but there you have it.